Good morning, good afternoon, and good evening. Welcome back to cellular respiration. Quick recap from the last video. Remember, we're burning up a molecule of sugar. We're burning up a molecule of glucose. When I say burn, that means get energy out of it. What is the energy in the form of? The energy is in the form of ATP. The first thing that we did is we took our 6-carbon molecule called glucose and we cut it in half. And we got 2 of these pyruvic acid things. I also got 2 ATP, that's what we're trying to make. And then I got 2 of these NADH things. NADHs go to the end, they go to step 3. Remember, cellular respiration is 3.5 steps. You're going to go to the end, step 3. This is money in my pocket. These are tips on the credit card. This is in my pocket. That goes away, so the only thing I have left is this right here, pyruvic acid, and that comes down here to step 1.5. Step 1.5, I start off with my pyruvic acid, and I'm going to cut one of those carbons off and release it as carbon dioxide. I now have a 2-carbon molecule, and where that carbon was, I put in its place something called coenzyme A. You know that enzymes help to make reactions happen, and I'll explain to you what coenzyme A does in just a second, but just hold on to that thought. 2 carbons plus coenzyme A, we refer to this as Acetyl Coa because acetyl just means 2 carbons. So the name literally means 2 carbons plus a coenzyme. And then the other thing that we make when we chop off this carbon is we make another one of these NADH things. We make another one of those tips on the card. This is another tip on the card. But notice, do I have a tip on the table on this one? I didn't make any straight ATP on this one, so there's no tip on the table. This is only just a tip on the card. All right, last thing. How many pyruvic acids do I have? At the end of step 1, I actually have 2 of these pyruvic acids. So what do I do with all of this step 1.5? I do the whole thing twice. I don't have 1 pyruvic acid. I have 2. So that means I don't make 1 carbon dioxide, I make 2. I don't make 1 acetyl CoA, I make 2. I don't make 1 NADH, I make 2. I've got 2 pyruvates. So I have to do this step twice. This process, called primer phase, it gets pyruvic acid ready to enter step 2. Remember, 3.5 steps, this is the half step. It gets it ready to enter step 2. This process takes place in the matrix. Now remember, when we talked about cells, we said that the mitochondria has goop inside of it called the matrix. Glycolysis, the first step, step 1, takes place in the cytosol. It just takes place inside the cell, no special area, just in the cell. The step 1.5 and every step after this has to happen in the mitochondria. Specifically within the mitochondria, step 1.5 occurs in the matrix. It occurs in the goop of my mitochondria. All right. Carbon dioxide we breathe out. NADH goes to step 3. The only thing we're left with now is acetyl CoA, and we take acetyl CoA to step 2 because that was the whole purpose behind primer phase, is to get pyruvate ready to go to step 2. The way it's ready is now it's a new molecule called acetyl coenzyme A. Step 2 used to be called the Krebs cycle, now we call it the citric acid cycle. I put both names up there because sometimes you see it both ways. It's also sometimes called the TCA cycle, whatever. Citric acid cycle. All right, full transparency, I learned it as Krebs. I learned it as the Krebs cycle, so I will sometimes call it the Krebs cycle. I will try to call it the citric acid cycle, but keep in mind, remember, I learned it as the Krebs cycle. It's been renamed since, so Krebs. I start off with that acetyl-CoA molecule from step 1.5. I start off with my Acetyl Coa. I'm going to add this to a 4-carbon molecule that was already there in the mitochondria. I'll explain where it came from in just a minute, but for the moment, just kind of trust me and work with me. It was already there. I'll tell you where it came from in a second. Four-carbon molecule. It has a name. Its name is oxaloacetic acid, but you don't have to remember that. Just remember it's a 4-carbon molecule. Four-carbon molecule plus 2-carbon molecule. 4 plus 2 equals 6. This molecule, the 6-carbon molecule, is called citric acid, hence the name, the citric acid cycle. When my acetyl is attached to my 4-carbon molecule, the coenzyme A pops off. That is what reaction this enzyme accomplishes, and that is getting those 2 carbons into Krebs cycle. My coenzyme A pops off. I like to think of coenzyme A as like a ticket, but not the bad kind of ticket, like a speeding ticket. I think of it like a ticket, like a movie ticket, or a bus ticket, or a plane ticket. What do those tickets let you do? Well, the movie ticket lets you go into the theater, and the plane ticket lets you go in the plane, and the bus ticket lets you go in the bus, on it, but you know what I mean. It allows you to enter something. What coenzyme does is it allows those 2 carbons right there to enter this process called the Krebs cycle, the citric acid cycle, all right? Once you're in the theater, do you still need the ticket? No, you don't need it anymore. The cool thing about this ticket is it gets recycled. It gets used over and over and over again. That's kind of what enzymes do. Enzymes are used repeatedly. They're not just a one-time thing. They're used over and over and over again. So this coenzyme A is going to go and get attached to another 2 carbons, another acetyl, and get reused to bring 2 more carbons into this process called the Krebs cycle. Well, now that we've got our 2 carbons in, what we're going to do is immediately cut one off. We cut off a carbon. What do we release carbons as when we cut them off in this process? We release them as carbon dioxide. If I have 6 carbons and I cut one off, how many carbons do I have left? 5. Four carbons plus 2 equals 6. That one's called citric acid. I cut one of those off and releases carbon dioxide. So I'm left with 5 carbons. You don't have to know this thing's name. We're going to do that again. We're going to cut 1 carbon off of our 5-carbon molecule. How many carbons are we now left with? 5 minus 1. We now have a 4-carbon molecule. Now, remember, when we talked about organic chemistry, you said when we draw it like this, this is that simplified version, which means there are oxygens and hydrogens on here that we're not drawing. There are oxygens and hydrogens on here we didn't draw. They're on here that we didn't draw. They're on here that we didn't draw. You just assume that they're there. So this 4-carbon molecule is not that one. Why not? It looks the same because of those invisible hydrogens and oxygens that we didn't show. But because this is the citric acid what? Cycle. What does it mean that it's a cycle? And what it means is, at the end of the first run, where am I? I'm at the beginning of the second. What happens when Monday ends at 11:59 p.m.? Tuesday starts at 12 a.m. Okay? So I've got to reform, and I've got to turn this 4-carbon molecule back into that one. And it actually takes about 3 or 4 more chemical reactions to do so. But I do it. And I said, remember, I'll tell you where those 4 carbons came from. Well, where did these 4 carbons come from? It's a cycle. It came from the last time I ran it. When I do this, when I send 2 carbons through the citric acid cycle, I get 3 NADHs. I get 1 ATP. What are we trying to make? We're trying to make ATP. And I get 1 of this new molecule we haven't talked about yet called FADH2. And I understand that we haven't talked about it yet, but what molecule does it kind of look like? Well, it kind of looks like NADH. It does look like NADH. What does NADH do? Well, what NADH does is it carries energy from these steps to the last step. So take a wild guess in the dark what FADH2 does. It's going to do the same thing. It just doesn't carry as much. NADH is a tip on the card. FADH2 is a cheapskate, and it's a smaller tip on the card.